Hey everyone. Hi everyone, it's Prof. K again, and we're going to do part 2 of writing and balancing chemical equations. So the first thing we want to do is talk about the learning objective. The learning objective for this video is to learn how to write and balance chemical equations in molecular, total ionic, and net ionic formats. And so today I'm going to walk through an example of a precipitation reaction that happens in water. So this is aqueous chemistry, and an equation that we might provide for you could be lead nitrate, which is aqueous, and calcium chloride reacts to form calcium nitrate and lead chloride as a solid. And so this is a molecular formula, which is something we've talked about in detail so far in this course, and in particularly the lab. But if we drew what's actually sort of happening in water, we could potentially write down the two molecular formulas of our reactants that are then undergoing some chemistry to form calcium nitrate, which is still in the water, and some precipitated solid lead chloride based on this reaction I've written. And so when we have this reaction, we can actually look at the individual components here and recognize that if something is aqueous, that means that when you add it to water, it falls apart into its component reactions. And so here, lead nitrate, if it's aqueous, forms lead 2 plus and 2 nitrate 1 minuses. Calcium chloride falls apart into calcium 2 plus and 2 chloride 1 minus. Calcium nitrate similarly falls apart into calcium 2 plus and nitrate 1 minus 2. And then the solid stays together. It hangs out as a solid. That's the concept of precipitation, which we've observed in some of the lab reactions we've done. And so if we go back to the drawing that I showed you, the precipitation reaction that I've drawn here would actually look more like what I've drawn here in solution, where our lead nitrate has split apart and the ions are sort of traveling separately from each other, even though they were added in some molecular amount. And so we can represent the molecular formula in terms of the ions here by splitting them apart. So when we get to our product of this reaction, our lead chloride is still a solid settled on the bottom, and calcium nitrate is what's left in solution as separate ions. And so this is a more realistic picture of what's actually happening in our beaker than our molecular formula describes when we tried to add it to the beaker. And so what we're interested in then, if we look at this, is how do we represent this in a chemical reaction so that we can understand what's happening more easily? So we have this notation that we can use where you can split up this lead nitrate into lead and nitrate and add that to a formula so that instead of just writing a molecular formula with everything still sort of attached as though it's a molecule, we can split it up into the ions like they look like in solution. And so this matches the picture of what's happening in your beaker better. So you have your lead, you have your nitrate, you have your calcium, your chloride, and that's reacting to produce calcium ions that are still hanging out in solution and nitrate that's still hanging out in solution, whereas our lead and our chloride combines to precipitate. And this reaction, which I've written here, is a complete ionic equation. And so what this tells us is it's a representation of all of the ions that make up those molecules we started with that are necessary to perform the chemical reactions. So if I start with an empty beaker, I have to add lead nitrate into my water. It breaks into lead and nitrate. I add calcium chloride into my beaker. It breaks up into calcium and chloride, and they hang out and they start to react, and out comes our solid, lead chloride, and what's left behind is calcium and nitrate. And so this helps us understand what's actually happening in the beaker and where everything is hanging out. And what that helps us do is move from this complete ionic equation to an equation that considers the ions that specifically undergo changes to form something new in our chemical reaction. So if we look up here, our nitrate doesn't actually do anything or change across our reaction equation. On the same hand, or similarly, calcium also doesn't undergo any changes. So the only atoms that change as we go through this process or that do any new bonding is lead, chloride react to form lead chloride as a solid. And so that equation is our net ionic equation. And so if you've seen the word net in other contexts, it might be if you have a bank account and you deposit $100 and then you take out $20, your net balance is 80. And so similarly, we're adding all of these chemicals into a beaker. They form ions, and then what comes out is our precipitate, and what's left over is those ions that are floating around that don't really matter here. And so what actually matters is what happened, what's the change. And so this net equation helps us envision what's happening in our system. And we actually saw this in our lab. And so we just did a lab looking at barium sulfate. And so we wrote that reaction in the procedure notes as barium 2 plus sulfate 2 minus forms barium sulfate solid. And so we didn't tell you that this is called a net ionic equation, but it is because it represents that we've added something like barium chloride to our solution to precipitate out barium sulfide. And so sort of hidden behind this net ionic equation in our procedure is all the things we had to add, which would make up a complete ionic equation for the system. And so these are two different names that we have for our system. And so we have a complete ionic equation, which is everything that we put into the beaker, how it's hanging out as an ion or how it forms a solid. And then from there, we can identify what actually changes in our system and get a net ionic equation. And what we lose between the complete ionic equation and the net ionic equation are the spectator ions. And so these are the ions on both sides of the equation that we cancel out to form our net ionic equation. So here, nitrate and calcium don't undergo any changes, which means that they're basically just hanging out in the beaker watching the chemistry happen, which is why we call them spectator ions. They're just spectators to the chemistry we're interested in. So we might ask you on problems to identify spectator ions, such as ones in this reaction, which basically just means if we can cancel them out on both sides, because they're not doing anything besides helping us get to what we want, because we had to add lead nitrate as a molecule so it could dissolve, form a lead ion that could then go on to do the interesting chemistry. And so as we've worked through this, we've described the molecular equation, which is what we start with and what we often see. And when we look at this, we dissolve what's aqueous to form a complete ionic equation. And then we cancel out any spectator ions to get the net ionic equation, which is what happened. And so these labels are what we use to help us understand what's happening. So if you're told this is a net ionic equation in a problem, that means that it's what actually happened. If you're told that something is a complete ionic equation, you want to start to look at it and be like, okay, which of these are spectator ions? Which of these can cancel out? How do I know what I'm forming? And I provided this formula and I told you that lead chloride was the solid, but the next video is going to talk about how you can recognize what might dissolve and what might form a solid. And so that's a skill that we're going to build. But before we start building it, we need to know, what are we writing? And is it a molecular equation, a complete ionic equation, or a net ionic equation? So hopefully this video helped, and we'll be working through some practice problems where we utilize this language and work on identifying different components of these reactions.